But really, that should just motivate us to make an SDP version of the Shirley-Adams proof system, which is what I'm now going to talk about. Could we come up with, can we throw semi-definite programming into the mix, since we know that semi-definite programming can be done in polynomial time? So let's look back at the Shirley-Adams K proof system, where we have an axiom of the form, any polynomial statement. This is slightly bad notation. It should be about any k out of the n variables. If it's true that this polynomial is non-negative on 0, 1 values, then you can take this line as an axiom. And here's a claim I want to make. This will be sort of motivation for our STP extension. I claim that this inequality, p of x1 through xk greater than or equal to 0, is true for all 0, 1 values of the variables, if and only if p, is, ignore this multilinearization for a second, if and only if p is the square of a polynomial. And, so what is this multilinearization? So if you square a multilinear polynomial, it might not be multilinear anymore because you have some squares in it. But this multilinearization refers to just whenever you see xi squared, just change it to an xi, which is a reasonable thing to do because we're all agreeing these xi should be 0, 1, and that's like a sound rule, like the square of a 0, 1 value is itself. Okay, so this, what I'm claiming is that this condition about p being non-negative is equivalent to it being the multilinearization of a squared polynomial. Let me give you a quick example about two variables. So this is a polynomial p of x1, x2. I just wrote it here. And first of all, I claim it's non-negative whenever the x variables are 0 or 1. So why is that true? Well, if they're both 0, this is 9 minus a bunch of zeros. That's 9. That's non-negative. Let's say if one of them is 1 and one of them is 0, you get 9 minus 5 minus 0 plus 0. So you get 4. That's also non-negative. Maybe the trickiest case, if x1 and x2 are both 1, you get 9 minus 5 minus 5. Uh-oh, that's -1 so far. Oh, but plus 1, so it's exactly 0. Okay, so this is a non-negative polynomial. And I claim it's the multilinearization of a squared polynomial. And here it is. I worked this out on my computer. Here's a polynomial. You square it, you get this long thing. But now also multilinearize it. So this xi squared, change it to an xi. And you see when you do that, you get minus 6x1 plus 1x1, which gives you minus 5x1. Okay, or look at this x1, x2 thing. We have minus 4x1, x2. But this x1 squared is really an x1. So this is plus 2 more, plus another 2 more, plus another 1 more. You get this plus 1, x1, x2. Okay, so this is like an illustration of this claim I just made. Okay, so let's prove this fact. Well, one direction is obvious. If you're a squared polynomial is definitely non-negative on all inputs because it's like the square of something. And multilinearization doesn't change things for 0, 1 values. So if you're the square multilinearization of a squared polynomial, you're definitely non-negative. So why is it the case that we have a non-negative polynomial? It can be represented in this sort of squared way. So here's the proof. Kind of harkens back a little bit to this Fourier analysis of Boolean function stuff. So even though p appears like a formal polynomial, think of it now as a function mapping k0, 1 values to a non-negative number. Now, as I mentioned before, every function mapping k bits to numbers has a unique multilinear polynomial representation. So keep that in the back of your mind. And this is sort of the Fourier analysis fact, but for 0, 1 values. Now, this is a funny statement. I claim that since p as a function, its range is non-negative numbers, the function square root of p exists. This is the function r, which maps a bit string of length k to the square root of p's value, which makes sense because p takes non-negative values. So now r is a function mapping k bits to real numbers. And so it has a multilinear polynomial representation. Let's call that the q that we're seeking. And so now q squared equals r as a function. They take the same values on 0, 1 inputs. Sorry, equals q squared equals p as a function, because q squared as a function is square root of p squared, which is p. And so the multilinearization of it has to agree with p as a polynomial. These two, the multilinearization agrees with p as a function, and so by this uniqueness property, they have to also agree as polynomials. Okay. So basically, the recipe for doing this, given p, is like take its polynomial representation, which looked like, p of 1, 1, 1 times x1, x2, x3 plus, etc. Square root each of the coefficients, and that's it. Good. Sorry. Did that make sense? Yeah, that's it. Okay, good. So with this claim established, let's just rewrite the definition of Shirley-Adams K. Let's say that Shirley-Adams K is a proof system where instead of saying, you have the true statements as axioms, let's say as an axiom, you get to have q squared is at least 0 for any polynomial q depending on at most k variables. Okay, and really, I mean the multilinearization of this. Okay, so good. So this is like a new definition of the Shirley-Adams K proof system. Same as before, same derivation rules. You can take non-negative linear combinations of the lines you derived. It's just I'm saying the axioms in a different way. I'm saying that the axioms you're allowed are, you can take any polynomial on at most k variables out of the n and square it and multilinearize it. And saying that that is non-zero is an axiom you're allowed to use. There's a question, square root the outputs, right? Yeah, on the previous thing, how to affect this, use square root the outputs. Good, so that's Shirley-Adams. And now, like I took away this question mark here, I can tell you about this SDP extension of Shirley-Adams. And it's called the SOS proof system. It also has a parameter, and different authors choose to write either k or 2k here. It's just a question of notation. I'm going to write 2k. But SOS with parameter 2k is comparable to Shirley-Adams with parameter k. And it's a generalization of this proof system, whereas an axiom, you can take that a squared polynomial is non-negative for any polynomial of degree at most k. So here, the polynomial whose squares you're allowed to assert are non-negative, or any polynomial depending on at most k variables. In this SOS proof system, you can have a polynomial that depends on all n variables. It just has to have degree at most k. And this SOS stands for sum of squares, and these ideas date back to Lasserre and Perillo from the year 2000. It's sometimes called the Lasserre proof system, but people have started to get stuck on the name SOS proof system. Okay, so this is, well, one thing is this is like only more powerful, okay, because every polynomial, depending on most k variables, can be represented with degree k. But now in the SOS proof system, you're allowed to have axioms involving all the variables as long as, it's like a square of a degree k polynomial. Now, what this is good for, we'll see later, well, shortly. But that's the definition. Okay, another fact is that if you take this parameter to be 2, so like k equals 1, so SOS 2, we're allowed to have as an axiom, the square of any linear polynomial is non-negative. That turns out to be exactly equivalent to the semi-definite program for Gomans-Williamson, that Gomans-Williamson analyzed for the max cut problem. Okay, so I'm not going to prove that, but this is nice for connecting it back to things we've seen, in particular semi-definite programming. So the semi-definite program for max cut is exactly equivalent in power, really in setup, to this version SOS2, where as axioms you can have the square of any linear polynomial. Okay, and now one more important theorem, which is sort of the reason we really like in combinatorial optimization, this proof system, SOSK. is that it's also automatizable in n to the order k time. It doesn't matter if you write 2k or k here, because I have a big O here. Okay, so in this more powerful proof system, still it's the case that whenever an inequality can be derived from the axioms, there's an algorithm that derives it in n to the order k time, which is polynomial time if k is a constant. Okay, there's a little asterisk here, because you need semi-definite programming to do this. It's sort of the semi-definite programming version of Shirley-Adams, and so this automatization algorithm uses semi-definite programming. And then there's like these, slight caveats here about, solving that to precision epsilon and polylog 1 over epsilon time and some big box constraints, but like, just don't worry about that. So that's great. So it means we have an even more powerful proof system that potentially can derive, it's more powerful than Shirley-Adams. It can potentially derive, more and more like tight bounds, true facts about the combinatorial optimization problems we care about. And still we can find these optimal bounds in n to the order k time, so polynomial time if k is a constant. Okay, so what is this good for? I mean, is this, truly better than Shirley-Adams? Well, on one hand, yeah, it is. As we saw, the Shirley-Adams, this SOS with K, SOS2 is equivalent to the semi-definite program for max cut, which was already good at like realizing, that in a random graph, the max cut is very close to a half and so forth. But here's another very classic example of what this SOS proof system is good for. So remember in the spectral graph theory lectures, we studied a lot this parameter of a graph, phi of g, the minimum conductance, which was sort of like the worst bottleneck in the graph quantitatively for the purposes of random mixing. So it's defined to be you like minimize over all subsets of vertices, non-empty and at most half the graph of this quantity. This quantity, the probability when you choose a random edge that u is in the set S, but v is outside the set S. So basically, it's the probability that in a random walk, you take like a random step and that you get outside of the set S. Okay, so if there's some set S where this probability is really small, like being inside that set is like a real bottleneck for the random walk. Okay, so that's why we cared about it a lot, this phi of g property, quantity. It's a number between 0 and 1. And I also mentioned that it's NP hard to compute it exactly. And in fact, it's NP hard to approximate it up to a factor of 10. Well, actually, that's not known, but it's de facto hard. Nobody knows how to approximate up to a factor of 10 or a factor of 100 or even a factor of 1,000. But here's a cool result of Aurora Rao Vazirani, typically called ARV, from 2009. Just degree 4 SOS does a good job of certification. Actually, maybe it's called degree 2 because the axioms here, you allow yourself that the square of any quadratic polynomial is non-negative. So in this proof system, it's a fact that whenever the minimum conductance is at most beta, this SOS4 proof system certifies that it's at most root log n times beta, order root log n times beta. Okay, so order root log n, theoretically this diverges to infinity as n goes to infinity, but so slow that, root log n is a very, very small number, even for enormous n. Okay, so it's pretty good. So, I mean, this is like almost like a constant factor approximation, or I should say certification algorithm for minimum conductance. Just as a technical point, I'll repeat it again. Remember, Cheeger's inequality lets you compute, it relates this minimum conductance to the smallest eigenvalue of the Laplacian. It says it's at most the square root of that. And you can compute the smallest eigenvalue of the Laplacian efficiently. But even though it's like qualitatively an approximation, it can't, you can't, put any specific factor here because, if beta is really, because the square root of the conductance itself could be like an arbitrarily small number. Okay, that was a weird digression. Never mind. The point is that this proof system, SOS4, is great for understanding the conductance of a graph. Okay, and just a reminder, you can compute this certificate in polynomial and n time. And for a long time, prior to this ARV paper, there was a linear programming-based certification algorithm that had order log n here. Okay, and after long last, they got it down to order root log n. Okay, so that hopefully illustrates the power of SOS somewhat. Come on, PowerPoint. Okay, so one cool thing about SOS, it's been sort of empirically discovered over the last, I don't know, 10, 15 years, is that actually almost all known certification algorithms for combinatorial optimization problems fit in this SOS system. So what I'm saying here is there's like many, many, many approaches to like heuristics for trying to certify bounds on combinatorial optimization problems or find approximately good solutions to combinatorial optimization problems. And sort of been discovered that like almost all of them can be sort of captured by these proofs in this SOS proof system. Any certification algorithm that's like polynomial time, almost anyone, can also, you can get the same quality certification with like SOS proofs. So they're sort of like, you know, the go-to tool whenever you have like a new combinatorial optimization problem, and in principle or in theory, you can say, try the SOS automatization algorithm on it. Hopefully it'll give you great certificates. And so it's always sort of like the algorithm to try to analyze and try to beat. What else is interesting is that it's humanly possible, although often very difficult, to actually prove statements about the failure of SOS to certify something. There's a question from the class. Do you know a natural example of an algorithm that does not fit, or at least is not known to fit? Yes, there's one very canonical example, which is the optimization problem of solving systems of equations over a finite field. For example, over F2 for simplicity. The field of size 2, so like, you know, solving linear equations mod 2. So this is like a constraint satisfaction problem. You have like all these variables, you're trying to assign 0, 1 values to them, and like the equations mod 2 are constraints. And what I'm about to say even applies if like every equation only involves 3 variables. So it's really like a CSP, like it's like local. Each constraint only constrains 3 variables in a certain way. And there is a polynomial time certification algorithm, like 1,1 certification algorithm, meaning one that can detect unsatisfiability correctly. And it's Gaussian elimination. It's like trying to solve the linear system. If you solve it, great, it's satisfiable. If Gaussian elimination fails to solve it, it'll certify that it's unsatisfiable. But it's a known fact, kind of interesting, that there are such linear systems where even every constraint involves 3 variables. It's like linear equations mod 2, where it's very unsatisfiable, but SOS, even with like k equal to 0.0001 times n, so k like really close to n, fails to certify anything at all. Just says like, well, the optimum is at most 100%. So these like linear equations mod prime or over a field are maybe the one exception to the great and glorious power of SOS. But what I'm saying is it's also possible sometimes to prove that SOS fails to do something. It's pretty tough to show that like there's no proof, like you for a specific instance that there's like no proof in this SOS proof system that its value is at most thus and such, because it's a very strong proof system. But thanks to like the notion of duality, which I'm going to mention at the end of this lecture, you know, showing that like there's no proof of something amounts to showing that like a dual to the STP or the LP is satisfiable. This is very vague high level, but like, you know, means you only need to find like some satisfying thing for the dual to establish failure of this SOS proof system. Okay, what I really want to get at here is though, like, these two facts taken together form a nice combination because, you know, we never know how to prove something is not dual in polynomial time. Okay, we cannot prove p does not equal np, and we have nothing like that. But in the context of like optimization problems, you can kind of say like, look, pretty much the best algorithm for certification for anything is this SOS proof system with higher and higher values of k. You know, that's almost all the algorithms fit in this framework. And so if you prove that, you know, the SOS proof system fails to do a good job on a certain kind of problem, that's like a really valuable negative result. It kind of says that like any of the heuristics people have thought about, or almost any of the heuristics people have thought about, are not going to work. So it's not like proving that something cannot be done in polynomial time, but that's sort of the best thing we kind of have these days for proving negative results in combinatorial optimization. And the most intriguing open problem in combinatorial optimization is this unique games problem, which I mentioned at the end of last lecture. And it's a big open problem. What does the sum of squares proof system do for unique games problems, or for this max bijection CSP that I talked about in previous lectures? In particular, it's open. Consider the following kind of task. For any large value of Q domain size, I give you a max bijection instance where the optimum is like very small, like the best assignment satisfies like 1% of the constraints. And your only goal in life is to satisfy that there's no solution that gets like 99% of the constraints. Can the SOS proof system with parameter 4 always do this? So just starting from axioms that look like squares of quadratic polynomials, can you always make this kind of deduction when it's true? This is unknown. And in the early days of SOS, people were really hopeful that maybe it was true. We still don't know, but maybe these days we're less hopeful that it's true. Perhaps SOS4 doesn't do this. It's just really, really hard to find a specific instance where SOS4 fails to do it. Okay, so for the, there's another question. Is there a special reason why the degree is 4, or is it just due to previous results? Good. So SOS4, you hear a lot about, because this SOS, the parameter is usually chosen to be an even number because it's like this SOS2k thing. So that SOS2k is like where your axioms are like squares of degree k polynomials. So sort of like SOS2 is the first one, SOS4 is the next one, SOS6 is the next one, and so forth. And SOS2 is basically always the same as like the basic SDP relaxation that you would always write down. And this is very well understood usually. Like it's not that hard to understand how well or poorly the basic SDP relaxation does for a wide variety of optimization problems. But like just the next rung up, SOS4, it's very hard to understand, very hard to analyze, at least currently. Maybe in 20 years we'll figure it out exactly. We'll really understand it well.